People online, if you can hear me, please say something.
Yes,
Morning,
we can.
Professor.
Thank you. All right, 9 o'clock. So we will get started. We are this week talking about intersection points. So just remembering how to do substitution and elimination and just kind of some basic theory stuff behind that. So solving systems of equations. In our next class, we'll look at some larger systems, like 3x3 systems. And then in the following week, we'll talk about using matrices to solve very large systems. So trying to get a bit more efficient with that stuff. So just before it. The preview homework that's been returned already. The main homework, we're working on grading that. The goal is to have it done for all the sections by the end of today. So at the very least before Thursday's class. So we'll have a chance to talk about it on Thursday after our questions or whatever. Okay, so last time we talked about here. Switching from the slope-intercept form into the other one, into standard form, and switching back. It's not too hard to switch back and forth. And then we talked about how to take some given line and then find various related lines. How do we find one that's parallel? How do we find one that's perpendicular or coincident? And then we looked at the equations for making cost, revenue, profits equations, and then we looked at a simple graph question with the iPhone to see what this looks like on an actual graph for a typical business situation. So intersection points, systems of equations, and we'll talk a bit more about break-even points at the end. So did I? Okay. So we did this last time. I won't go through this example again. We already did this work, but we had this one line, y equals 3x minus 1, and tell me the line that has the same intercepts but goes through a different point. So we figured out how to do that. Is parallel, so same slope but goes through this other point, etc. So we did more of that in the workshop last week, and that was on homework. So hopefully most people feeling reasonably comfortable with that. Now, okay. The other thing I want to spend a bit of time talking about before we go to today's material is a bit more about slopes and just visualizing slopes. Like, we had the formula and we could, find a bunch of points and then connect the dots, draw the line. But if you're familiar with slopes, you could just get any number and then right away be able to visualize mostly what it looks like. Maybe not perfectly, but a lot of it. So let's just kind of talk about that for a bit. So slope with a line through our origin, so through right here in the middle, and with the slope 1, what does that line look like?
It will be lying on y-axis, right?
It will not. Y-axis is an undefined slope. This is the slope of 1.
It's a line with a 45-degree angle from the x-axis.
Okay, yes, that is what we have. So 45-degree angle. So it would look like this. So remember our slope formula, m equals delta y over delta x. If it's a slope of 1, that's the same as just 1 over 1. So if we take one step right with x, we take one step up with y, or one step left with x, then one step down with y. That gives us this perfectly kind of 45-degree angle here. M equals 1. So this one, hopefully people are generally familiar with, but just visualizing some other ones as well. Right. So let's add these two kind of special cases, which I just talked about one of them a moment ago. So perfectly horizontal line on the x-axis. What is that slope? 0. 0. And then this perfectly vertical one. So this is our undefined m equals, right, question mark something. All right, so let's just think of a few different lines here and kind of see what they would look like. Let's start with first. This m equals 2. What is that going to look like? Relative to the one that we have now, relative to the m equals 1 line, what will m equals 2 look like? Okay, so more like up, steeper. It will be, make sure I got this correctly. Okay, so this is a slope of m equals 2 and a slope of m equals 3. It's more. How about 10? How about 100? Does it go like over? No. So 100, if these numbers keep going up, then they just get really, really steep like this. But they will not go past the y-axis. They don't like flip over or anything. They just go really steep. All right. And the other direction, 1/2, what does that look like? Reverse this way. Let's not say reverse because there's lots of reverses that we could mean. Okay, but mirrored. So if we talk about flipping, we could flip over the y-axis, we could flip over the x-axis, or we could flip over the line y equals x. All of those are common forms. So let's compare it to the line m with a slope of 1. If m equals 2 is steeper, then 1/2 is so like shallower, less steep. So it's going to look like this. So here's our slope 2. And then if we think m equals 1/3, 1/10, 1/100, same idea. We're just going to get really, really, really shallow lines like this. So hopefully we can just see the pattern that's happening here. If so, m equals 1, kind of 45-degree angle. Think about it that way. That one we can just remember. And from that, if we go this way, what number do we approach as we go this way? So if it was perfectly vertical, it would be undefined. What if it's like just one tiny step away from that, sort of infinitely steep? Not going downward. If we go like, so we had this line of m equals 100. If we just go steeper and steeper, what are we approaching?
Infinite, right?
Right, infinity. So just an infinitely large slope is almost vertical. It's extremely close to that. And going in the other direction, if from our line m equals 1 and it's going in this direction, what are we approaching?
0.
0. That's our perfectly flat one there, 0. So you can just remember that basic pattern, or if you can remember that, then if I give you a line with whatever slope, I could just make something up. Then just right away we can say, okay, it would look kind of like this or look kind of like that. And then the other half of this is for negative lines, I won't spend as much time on this part. M equals -1. So m equals -1. And if we go in this direction, what are we approaching? Okay, also 0. And if we go in, there we go. So -infinity in the other direction. So just you can just kind of remember these ones, and then it all just flips over like vertically like this down over the x-axis for all the negative values. So I know it's not like really hard to see this or think about it for straight lines, but if we were looking at some sort of curved line, find some sort of curved function like this. Then what we really want to be able to do is just pick any point on this line, like say right here, and just make a guess, well, what does the slope look like there? If we do that, then we just try to draw a straight line that touches and just say, roughly what is that slope? Not perfectly, but at least we should know positive or negative, and then greater than 1 or less than 1. This basic part is really key. When we do our calculus stuff later in the semester, this is exactly what calculus is, finding slopes at tangent points like this with tangent lines. But just being able to do this visually is very useful and will help you a lot. So here, approximately, what is the slope? Here, approximately, or here, or here. Just quickly say, okay, this is negative, and it's okay, it's less between -1 and 0, roughly about this value. Being able to do that will help a lot. So this is just some ways to think about slopes. All right, so let's get back to our stuff for today. We did a cost revenue profit example in our previous class, so let's do another one of those to get more practice with this, and then we'll come back to this example at the end of today. So cafeteria fixed costs are this. Here's the cost to prepare meals. Here's their sales price. So cost, revenue, and profit equations for this scenario. Take a moment, see if you remember what the basic forms of these formulas are. Try to do it without looking at your notes. Without looking at your notes, try to pull it from your head. That's how we practice learning the stuff. So basic versions of the formulas, and then with these numbers put in. So take a moment now. Okay, costs first. What is just the basic form of our cost formula? What's our symbol
Cost
for cost?
plus variable cost. Variable cost.
Okay, fixed cost, variable cost. Yes. What's the symbol we write for cost? That's the other side of it. So variable cost plus fixed cost.
Total cost.
Okay, so TC, total cost. You are going to see that a lot. TC. So please get familiar with that. All right, so variable cost plus fixed cost. And in this scenario here, what are the variable costs?
9.
9, just 9?
9
Wait,
multiplied by 5.
9 times 5? I don't think that's right.
I think it's 5Q, isn't it?
5Q. Right? Do we agree? Yes,
Yeah.
maybe. Okay. So variable costs here are your cost per item. Remember, cost here is not cost to customer, it's production cost. How much does it cost us, the business owner, to make the thing? So cost for each individual item times the number that we sell, and that's what we call Q. So numbers. Okay. So plus 1,500 for our fixed costs. Okay, so which TR, total revenue. Okay, so that's our P times Q. This one is our 9Q here. All right, so there's our total cost. There's our total revenue. And then if we combine these, profit, what's our basic definition for profit? In terms of these two,
TR minus CC here.
TR minus C. So we just take these two things, put them together, and Q minus 500 is for Q minus 4Q minus 1,500. I know we have a plus here, but there's a negative sign on the outside of the brackets. Anytime you're looking at a profit equation, when you start a new business, you don't start positive, you start with a loss because you've spent a bunch of money to start up the business and buy the land or whatever. So the constant for your profit equations should always be 0, or sorry, should always be negative, never positive. If it's positive, that means you've made money before you've ever sold anything, and that doesn't make sense. Okay, so there's our profit equation. So that's just the basic setup for the scenario. So now some actual questions. Give you these 3. So please figure out these 3 things. Cost of producing 100 meals per week. If revenue is that much, how many meals sold? And then what is the profit when we sell that much? You have the formulas, put in the values and figure them out. If you're online, you can write your answers into the chat when you have them. Okay, we're done. Yeah. All right. So question. A here, cost of producing 100 meals per week. The whole analysis here is a per week basis. So we just have our total cost. 5 times Q is 100, so 100. 100, so 2,000. Okay, so there's total cost for 100 meals per week. So question B here, not asking us for revenue, it's giving us revenue and asking us for quantity. So we just work backward with our formula. So 3,780, 3,700, 800 is equal to 9Q. So Q is equal to 3,780 over 9, which is 420. If you're trying to think of some no calculator strategies for this, you can just think 3,780 over 9. Just split it up into parts that are workable or easier to think about. So 3,600 over 9 plus what's left over, 180 over 9. Then this is probably easy enough to do in our heads. 36 divided by 9, that's 4. And just put the 2 zeros back. 18 divided by 9, that's 2. Add one more 0. 400 plus 200 is 420. All right. Need to erase some of that space here. Last parts for our profit equation, profit when 500 meals are sold per week. So profits is 4 times 500. Okay, minus 1,500. So 2,000 minus 1,500, $500. All right, so that's just a basic way of creating these cost, revenue, profit equations, and then doing some work with these. So again, a company is going to think about this sort of analysis, like, well, if we sold this many, how much profit would we make? And then separately, they do some market analysis and say, okay, like, can we actually sell this much? Like, how many customers realistically do we think will come in? Like that. So we'll come back to this at the end of today's class and add one more little bit to this. But for now, just some good practice with those formulas. All right, let's switch over to intersections of lines. All right, so let's just think some background stuff here. See if we remember our terms from last time. Ways that two lines in a two-dimensional system can interact or intersect. So this situation, what's parallel lines? Those are parallel. How many points of intersection? 0. Okay. Second case, they could be perpendicular, but in this case, this is just intersecting. Perpendicular is a separate thing. We'd have to look at the slopes, but we can just see, okay, 1 point of intersection. And our last case, okay, so infinite number of points of intersection. What's the name for this? Right, coincident lines. So those are the 3 possibilities. So If we're trying to figure out if there's an intersection, one of these three things could happen. So we just have to remember, like, these are the possibilities that we should be looking for. And of course, we care about intersection points because interesting things happen at them, like the profit and cost lines that we just looked at for the previous example. That's a break-even point where they intersect. That's a very useful point for us to know for running a business. So those are the possibilities. Just getting some terms out of the way here. Something like this is a system of equations. These are linear equations because they're just straight lines. There's no x squared. There's no 1 over x or exponential things or logarithms or whatever. They're just nice, easy, straight lines. So system of linear equations. We typically would refer to something like this particular one as two equations, two unknowns. Two equations because two equations, two unknowns because there are two variables in it that we want to solve for. So if we're trying to solve for this, then if we have two variables, then we need at least two equations to be able to solve for them, unless we have some weird special case. If you had three variables, you'd need at least three equations to be able to solve for some single point for them. Okay, so before we do the solving process, first, just if someone gives us a solution, it says this is the answer, how do we check that answer? Into which one?
What is the first one?
Doesn't matter which one.
Just one of them?
Yeah.
Yeah.
Okay, we have to check both of them. So it does matter. We're not choosing one. We have to check both of them because checking one of them just is checking if this point is on one of these lines. It could be on one of them and not on the other one. So one is not enough. We have to check it with each equation in the system. Only then do we know that we have an actual answer. All right, so we'll actually do that here. So this point 2, 4, is this a solution? We'll just take, we'll label these equation 1, equation 2. So take our points 2, 4, into 2, negative, write it out very thoroughly for the first one. Substitute in our values, 2 plus 2, 4, 6. Okay, yes, both sides equal 6. How do we interpret that result? We substituted the points into the equation, and what happened was that both sides of the equation were equal. What does that mean?
Which means it's true.
Yeah, it's on that line. So it's on this line. It's on equation 2. It is a solution to that one. So now we just check the other one. So our points into equation 1. Going to give us 2 times 2 plus 3 times 4. 12.5. We're going to get 16 equals 12.5. How do we interpret this result?
It's not
Not
another.
on the line. So it's a contradiction. We made this assumption that it was, but then something went wrong later. So our assumption is wrong. It is not on that one. So no for that one, yes for that one. So it's not a solution. It has to be on both of them to be a solution. So the checking process is the same as what we did for straight lines, except we just have to check on each part, not just one of them. So that's the simple part of this. So this one is not the solution. So we need to find our own solution. 3 different ways that we can do this, or Actually, there are a very large number of ways, but 3 really common ways. So we could just take these 2 equations and throw them on a graph and just look and see where the point of intersection is, of course. We could change these into slope intercept form, or we could do what we talked about last time where we just find the x and y intercepts. We just sort of ignore one of the values and then we figure out the other intercept pretty easily, put them on the graph and see what the solution is. It looks nice if you're making a presentation for a class or for your boss or something. Oh, it's a graph. Yes, it's visual, but it's not always like the perfect way of figuring out exactly what that point is. We should verify our work with some sort of algebra method. So 2 algebra methods, substitution and elimination are the 2. So we'll go through just one example of each, just reminding everyone about these basic approaches, talk a little bit about some kind of theory background, make sure we understand why these things work, because when we look at more complicated situations, we have to make sure we understand the basic versions first. So substitution. So just before we look at that, let's think about what our answers could look like. So we talked about the 3 possibilities: parallel with 0 points of intersection, just regular intersection with 1 solution, or coincident lines with an infinite number of solutions. What will each of those 3 look like in the algebra? Like if we do substitution and we solve for this, what results will tell us that it's perpendicular, or sorry, that it's parallel, or if it's coincident? What will those 3 things look like in the algebra?
In parallel, we would have the same slope.
So we're not asking what do the slopes look like. We're not comparing the equations. Let's say we just go through the process of trying to find the solution. So we do substitution method or whatever. What is the final result that tells us, oh, these are parallel? What does it look like? Not the same number. So that's just if we have 2 separate equations and we're comparing them. But when we do this sort of like a system of equations, we don't always like find out exactly what the slope is. Yeah. We don't need to do that. So that's, again, sort of the graphing style approach. This is just with the algebra. Okay, so 3 things that could happen. So first, 0 solutions. That's and for just 2 dimensions, that means we have a parallel result here. We'll get some kind of impossible results. We'll try to solve for the x and the y, but then the x and the y variables will disappear. They'll be canceled out, and we'll be left with just something that doesn't make sense like this. That's how we know we have no solutions to our system. If we get 1 solution, then it just kind of works out nicely. Here's the x value, here's the y value. That's probably what we would usually expect. The other one is if there's an infinite number of solutions, if they're coincident, then we'll get something where there are no constraints. So again, the 2 variables will just sort of disappear as we do our solving. They'll just be canceled out. And we'll get something where it's 2 constants, but the 2 sides are equal. So here, 2 constants, but not equal. Here, yes, equal. So the first one, that's a parallel situation. Last one, that's a coincident situation. So that's what it looks like in the algebra. When we go through our solutions, again, we need to be able to interpret our solutions correctly and know what thing means what other thing. All right, so let's actually do the solution here. So substitution, I've written all the steps out on the side. If you're not familiar with the term, once you see it, it'll probably feel very familiar. But we'll just kind of go through the steps I've listed out. So again, equation 1, equation 2. So substitution, the big things are isolating one variable and then substituting in that variable into the other equation. Just so you know, usually when we talk about math, instead of substitute every time, we just say sub as a verb. So I am going to say that for the rest of the course because that will save me a lot of time. So isolate x in number 2. That looks like the easiest one to do. So we don't we could isolate any of these other ones. But if we do x in the second equation, we don't have to multiply or divide by anything. It's just easier. So isolate equation 2, rewrite as x equals 2y minus 6. Okay, done. Then we substitute into the other equation, take that x value, substitute it into equation 1, which will give us 2 times our x value, which is this 2y minus 6 plus 3y equals 5. And then one equation, one unknown, one variable. It's very easy to solve for y. We just do some simplification and we figure out what that is. All right, so 4y minus y equals 0.5. We'll get 7y is equal to 24.5. So y is equal to? Which is? Okay, so just again, some no calculator strategies. Let's get rid of the decimal here and just double everything. 14 and 49. Then we just divide everything by 7. We can see that 2y is equal to 7. So y is equal to
3.5.
All right, so we have solved for y. That's half of what we wanted to do. From this point, again, I'm sure we're comfortable with this. Now we've solved for that variable. We are back, or we're over here now. Fourth step, we'll take that one, substitute back into either of our original 2 equations, and then solve for the other variable. So let's take our y, substitute that into equation 2. So negative x plus 2 times 3.5 equals 6. X plus 7 equals 6. X negative 1. X is equal to 1. So looks like our solution is 1, 3.5. And we can check our solution very easily by just substituting into our original 2 equations. Okay, so that's the substitution methods. Of the 2, substitution and elimination, I usually find students are more comfortable with substitution. So it works. It's not too complicated. Again, I'm sure most of us have seen this before. So just some little notes here. Substitution is especially useful if we have 2 different equation types. Like one's a straight line and then one's like an x squared or something. Substitution works very nicely for those situations. But if you have a larger system with 3 or 4 or 5 equations and you try to do it with substitution, it takes forever. That's not very fun. So we'll actually do that once in our next class. But elimination is definitely the one that's more useful for larger cases. So that's going to be a big thing of what we do with our matrices in the next class, sorry, next week. So want to be familiar with this one as well. So elimination. We'll do the same system of equations with elimination. Just before we do that, there we go. Let's just quickly talk about some background theory stuff about what we can do with elimination. So elimination, there are two basic operations that we can use. First one is we can multiply or divide any equation by a constant, just some number. So equation 1 here, 2x plus 3y equals 12.5. Well, I can just multiply both sides by 2 and say, okay, we get 4x plus 6y equals 25. Right? So just multiply both sides by the same thing. It stays balanced, so no problems. We can divide both by something, by 3, and I won't write it out, but that's probably not very controversial. The other one, some people just kind of like forget that this is possible even. So, or just kind of are a bit confused about why this works. So I say that we can add or subtract not just a number, but we can add or subtract one whole equation from another whole equation, not just plus 2 on each side or something, but we can do this and take the whole first equation and add it to the whole second equation and get something like this. So if we were to add these parts, so 2x minus x would give us x. If we add 3y plus 2y is 5y. If we add 12.5 and 6, we get 18.5. So I know this is not useful. We'll do it a little better on the next slide when we actually try to solve this thing. But for now, just we can do this. On the other one here, we could also subtract the two equations from each other. 2x minus negative x, so 3x there. 3y minus 2y, so y, and 12.5 minus 6, so 6.5. So does this work? Like, is this a mathematically valid thing to do? Am I breaking some math rules by adding two equations like this? Okay, why does it work? I can add just a constant, like I could take one of these and just say like +1 on each side. Why can I add whole equations to each other? This seems weird. They do, but even if they were completely different, even if I had totally different variables, I could still do this. So there's something a bit broader.
Because we're like trying to find an intersection point, right?
That's the goal, but that doesn't mean that this process is valid. We have a different reason for saying that it's valid.
Because they are on the same graph?
They don't need to be on the same graph. They could be totally different things and we could still add them together. I don't know, the way each country teaches math, it's a bit different. Some places they just say, the teacher just says, hey, do what I do, just memorize this. Some places they'll actually like try to explain some background and stuff. So just take a moment to do this. Let's say we have two equations. One equation is A equals B, and we have a different equation that is C equals D. Okay, so I'll say I'm going to take the first equation, A equals B, and I'm going to add C to, got ahead of myself. I'm going to add C to both sides. That's okay? All right, but this C is the same as D, or it's not the same, but it is equal to D. So I could just rewrite that to be A plus B equals C plus D. That seems okay? Yeah. Okay, so what I did was I just added the two left sides together and the two right sides together. So just basically it works because it stays balanced. This thing is an equation, it's balanced. The left side and the right side are different, but they are equal to each other. If I add equal things on both sides, it stays balanced. So that's the basic idea. We can also even multiply one equation times a whole other equation, because again, it would stay balanced. We might see that a while later, but if both sides are balanced, then we can just apply both of those to some other equation. We're not like breaking any sort of math rules or whatever. So just to convince you that, yes, this is a real thing that we can do, and it does work. All right, so we'll do elimination with this here. Same two equations, so we should get the same result. Let's just make sure that happens. So step one for elimination is we might need to rearrange. What we want is our two x's to line up, our two y's to line up, or whatever the variables are, and then the constants to line up. They should all just kind of be arranged in the same way. Here, they are already, so done. We don't have to do anything special there. Right? The next step is solving for one variable by eliminating the other variables. And we do this with our two operations, multiplying or dividing some equation by a constant, and then adding or subtracting the equations to do the eliminating part. So if you look at this, which variable would you eliminate?
Y.
Y? So why would you choose that?
Like, I know.
Okay, people, okay, in class? Okay, so we can do both. Which one seems easier? Okay,
X,
y, x.
X,
All right, so let's write these out. Let's say if we wanted to eliminate, I'll write this out with the x's first and then with the y second. So if we want to eliminate x, then it looks like we can keep the first equation as is. And this, what would we do with the second equation here?
2 times the second equation.
So multiply that by 2. So 2 times the second equation. So that's negative 2x 4y equals 12. And then we are adding these. Why are we adding?
Because when we add 2x will be minus 2x, and then we will eliminate 2x.
So here we have opposite signs. One's positive, one's negative. If we add, they disappear. If they were the same sign, then we would subtract to make them disappear. But we want to eliminate the x's. That's the goal. So if we just do this addition here, we don't need to write this step out, but I'll just do it for thoroughness here. 0x, okay, that's what we wanted. It's good to confirm though that it does actually happen. Okay, so 7y here. So 3y plus 4y, 7y. And our right side, 12.5, 12, 24.5. That's the thing that we just had with the substitution one. I'll skip the steps here. That's our 3.5. Okay. And then from here, it's the same thing that we did with substitution. We put the y into either of the original two equations, but again, equation 2 seems a little easier. So negative x plus 2 3.5 equals 6. So dot 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 x is equal to 1. So we could have done this targeting the y's instead. We could have eliminated the y's. Here. So if we did this trying to eliminate y's, what would we have to multiply our equations by? If we want to eliminate y, what would we do?
We had to multiply the first equation by 2 and the second one by 3.
Okay. So we'd have to multiply both of them by something. If we are good math people, then we are lazy. We don't do more work than's needed. So if we just multiply one of them by something, we don't have to multiply the other one. We save ourselves time. Also, if you're doing more arithmetic, you are increasing the chances that you're making a mistake somewhere. So simpler, if it still works, there's no reason not to do it. So find what's easiest. Again, when we get to our matrices stuff next week, efficiency is absolutely the goal. So don't make more work for yourself than needed. But we are eliminating here. Just choose your target, then multiply or divide to make one of the coefficients pairs line up, match with 2's. Then we just add or subtract the two equations to eliminate. The rest is the same as the substitution. So just reminding you the process and theory stuff, the goals, strategies, everything. All right. So some just quick notes about eliminations. Elimination method. Very nice, very useful if all the equations are of the same type, which does happen a lot. So widely usable. Just this kind of, I don't know, regular elimination like we just did can also be pretty slow if we have a large system, except if we rewrite them as matrices, and then we can actually do a whole lot of steps at the same time. We'll get to that next week and show you how to do that. So that's nice because if we have really large systems with like 5 different variables or something, if you try to do that with substitution, you're going to fill like 3 or 4 pages of work and you're probably going to make a mistake somewhere and you're not going to know where. It's going to be a lot of work to sort out. So matrices keep things very organized and let you go a lot faster, and it's easier to catch mistakes. So we'll see the advantages of that. So just in case, if you're someone who learned both of these in school and one of them you didn't like, so you just forgot that one, please be familiar with both. They're both practical. We're going to need both. All right, so just quick summary. Graphing looks nice, not super precise. You want to verify your solutions with algebra. Substitution or elimination are the methods. And then these are the possibilities. When we do the algebra, we could have 0 solutions. So an impossible result, like we said, 3 equals 6 or something. Not possible, that means no solutions. 1 solution, you just get a solution for each of your variables. And then infinite solutions, you get to something where the variables disappear and you have no constraints. It could be like a 1 equals 1 or 0 equals 0 or something. All right. Let's just do some practice here. So these two, I know the one on the left looks like it's perfectly set up for elimination, but let's do substitution here anyways. And on the rights, we'll do elimination. So I'll give you a moment to do these on your own, and then we'll talk about them together. Okay, let's take a look at these. The one on the left, substitution. Which would you isolate? Which variable in which equation? So x in first equation. That looks like the easiest one because we don't need to multiply or divide by anything. That's already has a coefficient of 1 in front of it. So equation 1, we will rewrite as x equals 4y minus 4. Substitute into the other one. Equation 2, so negative 3 4y minus 4 plus 4y equals 0. So negative 12y plus 12 plus for y equals 0. So this turns into gather our terms here. We have 8y, so negative 12 plus 4, move that to the other side, 8y, and then 12 here. So y is equal to 3 over 2. Our other variable. So we'll take y. Which one do we want to substitute that into? Second one? Okay, why the second one? For fun? Random?
Because we eliminated in the first one, maybe we made a mistake. That's why let's check on the second one.
So we kind of combined the first one and the second one together. That's effectively what we've done in this step. So our solution is already dependent on both of them. So it doesn't really matter which one we go back to in that sense. We just want what's easier. First one, why the first one? Why is it easier?
We don't have to multiply, so we don't have to do so many multiplications there.
Okay, two people trying to speak at the same time. So first, we have a dividing by 2 and we have a multiplying by 4. So the fraction will disappear, but that will happen in both of them. But then here, the x, there's no coefficient. We don't have to do, it skips a dividing or multiplying step. So it's a little bit easier, but both of these are not especially hard here. So into equation 1, so x minus 4 times 3 over 2 is equal to -4. Okay, so that's x minus 6 equals -4. So x equals 2. And then our solution here is 2, 3 over 2. Okay. The one on the right, our elimination question. Let me write our labels here. Equation 1, equation 2. Which variable would you eliminate?
Why?
Okay, so the y's, why that one?
Because in the second one, we don't have to multiply or divide.
Okay, so we would not need to multiply the second equation. So we can just multiply the first one. We can make the coefficients line up. So equation 1 times what?
3.
3. Okay, so 3 times equation 1, which will give us 9x plus 3y equals 15. And then equation 2, don't need to multiply. 2x minus 3y equals 7. Are we adding or subtracting these?
Adding.
Adding them. Okay, so again, we have the same coefficients here, so those will eliminate, but we have opposite signs, so we need to add. So if we do that, we will get 11x and then 0y. I won't write that, and we get 22. So x is 2. All right, and our x, which one do we want to substitute this into?
The first one.
First one, yeah, looks a little easier, but yeah, both not especially hard. So 3 times 2 plus y equals 5. So that's 6. 5 minus 6, y is -1. So solution here, -1, 2. Yeah, sorry. Wrote that in the wrong order. 2, -1. Okay. All right, so two solutions here, substitution, elimination. Our textbook has a whole bunch of practice questions on these. If you're feeling like it's maybe been a while, you kind of forgot some parts of this, go through and do some of those practice questions. These are the easiest possible form of these questions. So if these ones were maybe a little tough or took you some time, do some practice so you're familiar with them, because we're going to look at harder things soon. All right. Any questions about these? We're good. All right. So last thing for today, coming back to that cost, revenue, profits example with our cafeteria. So we made these equations. We figured out these things, A, B, C here. But now we have a new question. Break-even point. What is the break-even point for this scenario? So let's first just define again, what is the break-even point?
Is it
Okay,
when
we start making profit. All right, so we will mathematically. Okay, so we'll leave it as sort of specifically 0. And then if we're above that break-even point, then we are earning money. So where our profit equals 0. So if we remember, or it's down here. So our profits equation is total revenue minus total cost. But the break-even point is where profit is exactly 0. So right. So we'll get to the Q in just a moment here. Just want to show some explanation of the way it typically looks. So profit is 0. So 0 then is total revenue minus total costs. And then if we just do a little bit of rearranging here, total revenue equals total cost. So total revenue does not equal total cost all the time. It's only at this one special point, which is our break-even point. So this often you will see break-even point as like a formula or whatever described like this. But just remember, it's not all the time. It's only at this point, and it's because that's where profit is 0. We just do some very simple rearranging with this formula here. Okay, so not all the time, just for the break-even point. All right, if we want to actually figure out what it is for this scenario, we have our total revenue, we have our profits equations, revenue and our cost equations, not very hard to figure out. So right now, take a few seconds, tell me what the break-even point is. All right, what's our number? 375, he says. Okay, let's check that. So total revenue is on the left, so that's 9Q. And on the right side, we have our total costs, which is 5Q plus 1,500. So we rearrange. Q equals 1,500. Q is 1,500 over 4. Again, if this is maybe a little confusing, we can just sort of remind ourselves, just do this in steps. Well, 750 over 2. And then maybe from there, it's a little easier to do dividing by 2 one more time. Yes, 375 as our Q value here. So we could have also found our break-even point just directly from our profit formula, because in here, this 4Q minus 500, and if we say that our profit is 0, then that looks the same as this step over here, right? So if we do the TR equals TC, or if we do it from the profit equation, it's the same thing. It's just a slightly different way of looking at it, but we'll get the same result. So if we have a profit equation, we can find the break-even point. If we don't have a profit equation, we just have cost and revenue equations, we can still find the break-even point. Right. Okay. So nice simple scenario here. Find the break-even point. Questions? All right. So I think that was pretty much everything. So just wrapping up here, we can find points of intersections. We can solve systems of equations, because often that is just finding a point of intersection, and break-even points for a simple business situation. If you want practice on each of these things here, these are the exact exercises in the textbook for each of these parts. I'll have a list on our classroom page soon. We'll go through just a bunch of these in the workshop this week. I'm still working on choosing the particular question, so I'll have that in a little bit. But they're all chapter 4.1 in our book in these parts. Our book is not really a business textbook. It's more focused on just kind of general math stuff. So it does not have a lot about break-even points, but it does have a little bit. So there are these two questions. But yeah, our book is more of a general math book, so not so much of that. Right, so next class, we'll be looking at larger systems, 3x3 systems with substitution and elimination. And we'll see that they're very annoying and they take a long time. And then that will prepare us for matrices next week. You guys know that there's a holiday coming up next week, nice long holiday. Before you get too excited, just remember that, or know that for Korean universities, there are no canceled classes, there are only delayed classes. So next class, I'll talk about what our makeup class schedule and plan will be for those, but just be aware that we will have to actually do something with those. We can't just forget about those days. All right, I think we're done. The attendance sign-up papers, I'll put them up here. Please sign before you leave. And I will see you on Thursday. Goodbye, everyone.